So this is a little tutorial to learn about how to use dynamical systems ideas in infinite dimensions, exemplified by fluid dynamics. It's part of Chaos book. So what's plotted here is there is a system which has 64,000 dimensions. I will actually look at it. 61,506 dimensions. And what it is that if you subdivide your volume in state space to little cubes, because you have to put it on computer, and computer cannot take infinitely many data points. So you make a grid and put a mesh, and then you rewrite your differential equations as equations acting on the cubic neighborhoods, or hypercubes. Then each, well, they're not big they're three-dimensional hypercubes in this experiment. Then each one of them describes a fictitious massive particle, because it's a volume of mass that's being carried around by the flow. So each one of them, has some density of mass, for example, depending whether fluid is viscous or not. But if it's inviscid, then they all have same density. So each one of these fictitious particles, which is your fluid divided in 1,000 or 10 to the 6, or 64,000 little special degrees of freedom, which describe how they move around. That's your state space. Now, that's not a good representation of state space. So you learn about Fourier analysis and representing this in terms of Fourier modes, etc., which is more natural way to describe it. So there's lots of technology in between, but the main thing is you're in high dimensions, because fluid is in principle infinite dimensional, and any field theory is infinite dimensional, but any computation is finite dimensional. It's just that today we can make them, million dimensional. Typical calculations that grad students on the 3rd and 5th floors are doing, that typically 100 to million dimensions, and other people do, people who do weather do higher dimensions than that.
A question related to that. So how do you know that 1,000,000 dimensions is enough?
Yeah, you're absolutely right. This is a cheat. When I say it's 64,005, that's the number of degrees of freedom that's used in particular set of calculations. So what we do is we set ourselves standard. For example, we want to know, it sounds crazy, but that's what we actually do in this particular case. We want to know every velocity to precision in one part to 10 to the 6. Then to know where this precision is attained, I discretize my volume by 32 lengths in each direction, let's say, do a calculation of velocity fields, then I double all the dimension, do the calculation again. And if I can show that all the errors in these calculations are smaller, 10 to the minus 6, then I stop there. I don't discretize it any further, because I do not need more precision to attain the precision I need. So the number of degrees of freedom depends on what precision you need to attain in your calculations. Now, why do we need, if you engineer and the velocity of the fluid is, 10 feet per imperial gallon or whatever, engineers think about, a percent or 10% could be good enough, But when you're trying to find these unstable solutions, you have to be very precise, because to get an unstable solution, you have to control your trajectory for sufficiently long time that instability doesn't explode it to order 1. So that's why, to do these calculations, we need much higher precision that was traditional fluid dynamics before the subject became part of fluid dynamics. And the 64 is just a reflection of that. It's an empirical number that says, all my errors are under control. If I have 64,000, then you discover that if you go to million dimensions, you get nothing. You still have the same kind of precision. So there's no, there's a minimal number of degrees of freedom, meaning the minimal number of little volumes that you're discretizing your problem in that's needed for desired calculation. So there are two things going on. No mathematician has bothered yet to prove that any one of our solutions is exact solution. So as long as nobody puts his name on it and it becomes a theorem, we might be wrong. Our solutions might turn out to go away when I increase precision by 12 orders of magnitude or something. So that's reality of living in our world. Now we are not very worried because in anything that we want to describe, noise of various kinds is much larger than the number. So this is not our problem. But to prove it as a theorem, it remains unproven. Now the proofs are very boring. The way we find the solutions in these cases, it's called Newton method. So just generalization of a method of finding a root of one-dimensional polynomial. You get a good guess, you compute derivative close to the guess, you get better guess, and you show that that sequence converges to the exact solution exponentially, and that's a proof. When Newton method works, what it does is you start your guess in some volume in neighborhood of the correct solution, and Newton method maps this volume into smaller volume. That's called, mapping cones into cones in technical language. And the moment you prove this, you know that you will end up in a point if you can prove. So that's what some mathematician would have to prove. We would have to give them our numerical solution, and he would just have to check that what we do actually converges, but we know it converges. So nobody's bothered to do it. So it's not rigorous. We have found equilibria, so exact solutions of Navier-Stokes equations that describe fluids in 64 blah, 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 thousands of dimensions. And if you compute velocity stability matrix, this is 64 times 64,000 dimensions, a big matrix. But it has some big eigenvalues. It has lots of very, very small eigenvalues. And the way you distinguish big from small is you start computing eigenvalues, and you find that your solutions, which I'll show in a second, have very few. So every color here is a different solution. It's eigenvalue. So for example, this thing called lower branch has only one real expanding solution. And then there's the 64,000 contracting or negative solutions. But then you immediately find there are other solutions. So similar with this star here, one here, but it has a complex pair negatively. And you immediately find that you find lots of oscillating solutions, because even for the unstable spiral out solutions, you find lots of pairs. Now, what is this? What am I showing you? So I'll give you executive, elevator pitch, very long ride in an elevator, 10 minutes. So this I designed for professors because they don't have time to learn anything. But if you have some time, the real story is about 1 hour of your time going through it. And I'll quickly explain, what is significance of these eigenvalues I just showed you. First, I showed you one can compute them. It's highly non-trivial. It took a couple of years to figure out how to do it, but now we can do it. you can download this channel flow, and you can do it at home on your own laptop. So the experiment that is one of the very easy fluid dynamics, and easy in quotation marks, but very clean fluid dynamics experiments is taking two walls and putting fluid between them. So there are two parallel glass plates, or if you're looking at this fluid. And then what you do is you shear the fluid, that's called wall shear driven fluid, by moving the top plate in the red direction away from us, and bottom plate in the blue direction toward us. And now the color that's colored here, it's very hard to color three-dimensional volumes. So we take a cross surface halfway between the two planes, and we color pieces of fluid that are moving toward us blue, and the ones that are moving away from us red. And one experimental and also in your own experiments knows that when you shear sufficiently rapidly moving this plate, the turbulent flow will set in, the water between the plates becomes turbulent. And that you see, by the fact there are all kinds of structures that show up. There's some kind of rolls and streaks and things that wiggle, etc. And they're turbulent in the sense that if you just sit here as a graduate student and wait 10 hours, you'll never see the same thing twice, just like when you look at the clouds. At this point, I'll stop. Does this make sense to you, or anybody wants to ask a question? Because that's a physical setup of a very high dimensional problem. It's high dimensional in the following sense.
Thank you.
What do you say?
Question.
What do you say?
I just have a question about this figure here. You mean this figure you mentioned, we are going to put a shear in the fluid by moving the top in one direction and the bottom in
Correct.
another. Okay, but I mean, the whole thing is put in a big fluid thing, or how can you move the bottom? The fluid is something of hold.
Yeah, so I'll show you the experiment. So this is in Göttingen, and it's moved to Vienna since. So here is the experiment. So this is a pretty big machine. I'll show you a human. So this is Mark, my friend, leaning on the experiment. And this looks like an old-fashioned printing press. It has two big cylinders here. And then at these little windows, there are four thin cylinders that you don't see. And then there's a plastic sheet that goes over the cylinders. So if they're rotating in one direction, this plastic sheet is against the glass moving to the left, and the opposite one is against the other glass moving to the right. So do you see that? Do you understand how that will work? So that enables you to have an infinite, continuous, controlled shear between the two walls. And because the turbulence is happening on 10 centimeter scale, there are effects that happen at the edges of this window, but you don't feel them. The turbulent fluid is not aware of them if you're looking someplace in the center. So what you do in experiment, you put in the fluid, you spray some, pollen or little glittery particles, and you shine 3 different lasers on it, and you have cameras, and you produce 3-dimensional picture of, if you have a liter, at every cubic millimeter, you find out 3-dimensional velocity vector where that cubic millimeter is moving. And that's what's shown in the other plot. Are you okay?
Yeah, yes, thank you.
Let's see, I have to, sorry, I have to go back. So what's shown here is not the experiment, it's a numerical simulation. But it's, the same thing. So this is now sideways rather than vertical. That just has to do with building the machine. But the basic thing is that at every little volume of the fluid, there's a 3-dimensional vector of which, 2 components are plotted here. So you see these little vectors. These are local velocities of the fluid. And the experimental data is much harder than numerical data, but it looks very similar. Naked eye cannot distinguish. These experiments are so amazing that you can distinguish it. So that's an example of very high dimensional system. And since 100-some years, the idea is to say, this is so complicated, I can only make some statistical description of it. So that's what lots of mathematicians and physicists have been doing until roughly this millennium, where it became possible to see the fluid in detail and to experiment, both experimentally and numerically. This is all, at most 20, 30 years old, and most of it's much newer. And so now you have a responsibility. When you look at this, this doesn't look statistical at all. Same thing with clouds. You see all kinds of shapes. So you're supposed to describe, if you're an honest person, you're supposed to describe what is it that you see, rather than just taking some stupid average and publishing physical letter, as physicists tend to do. So this is the system you're trying to understand. And this is a typical simulation, which tells you that it's turbulent in the sense that I can run this until cows come home and I'll never see the same thing again. So we are supposed to describe that. Now it's dynamical system because we have equations of motion, they're deterministic. We are not assuming anything about noise. So we are supposed to be able to find what this system does, right? Because we have the equation. That's been a big challenge remains a big challenge. You can get $1 million if you do something about turbulence for a Millennium Prize. But, that's what it looks like. So now, in this course, we teach you have to find equilibria. Now, your equilibria are in 1 or 2 dimensions. So you typically, any child can find those equilibria. You just, pick up some program, you plot it in the plane, you compute them as well as you want. Sometimes you can get an analytic formula, but nobody cares. The important thing is you get it accurately enough. So then, very recently, so this was done in 1990s and everything else was done in 3rd millennium, people started finding equilibria of infinite dimensional flows like flow in Planck-Webb. So simplest equilibrium has been known since the invention of Navier-Stokes equations. It says that if you move the flow 2 volts, you can move each layer of the fluid at different velocity in such a way that velocity goes from -1 to +1. And that's called laminar flow. They're just layers going on top of each other. The first not trivial one is actually quite interesting because if you remember what I showed you in simulation, you see things that looks almost regular, but when you look at it closely, it actually wiggles. And there is another solution which wiggles a lot, and it looks like what you see in the flow all the time. Now, as you change the parameters of flow, parameter of flow is just velocity of the flows. These guys get to look more and more like each other, and they actually collide and disappear. So it turns out this infinite dimensional flow has a saddle node bifurcation, and it has two solutions which close to each other are indistinguishable when they get born, but then as you increase the stretching, this guy called upper branch gets more and more distorted, and the other one gets, not as distorted. And that's what all we knew about this in the year 2000. We didn't know more. Now we are very good at it. So there are, infinite many solutions, and they get more and more complicated. And if you show this picture to fluid mechanician year 2000, it take half an hour to explain it to them that nothing is moving. This is equilibrium. This means there's a solution where there's velocity of field every place pointing some nonlinear way. Look at this guy. But they are not changing in time. It's equilibrium solution. Yeah, that's what it is. And that's what dynamical system says you should find. Okay, great triumph. Took a couple of years to do this. Then, if you have this, you should be able to find limit cycles or periodic orbits. They're also invariant solutions. So that was a big deal, finding these things, because what's the problem about finding a limit cycle in 64 dimensions? Imagine you're in this famous lecture room where several people are right now. You have a boomerang and you throw it and it comes back into your hand. Now, that takes a lot of skill. It can be done. Now, if you're in 4 dimensions, it'll be much, much harder to make sure that boomerang comes back, because you would have to control 4 different velocities very accurately, because errors tend to grow even exponentially as the boomerang goes around. And if you do this in 64,000 dimensions, nobody believes it can be done until our millennium, and now we do it routinely. But once you find it, it looks like this. So here is the simplest solution one can find, which is periodic in time. So what's going on, time is being shown, and we went to 99 units of time. And then when we get there, it just continues at time equals 0. Now, if I didn't tell you this was a periodic solution, it looks turbulent as hell, because it does this and wiggles, etc. And if I observe it for 95 minutes of intrinsic time of the simulation, I would never know this is periodic. It just looks like all the turbulent solutions. So that's a pretty big deal. And there are lots of them. So this is what it looks. But if I show you the one that I showed you again, it'll look just the same. This happens to be turbulence, never the same. The other one is periodic in time, total miracle. But that's a periodic orbit we've been studying in 2 dimensions, and we'll study it in 3 at the end of this course, and that'll be all. But you can see them in arbitrarily many dimensions. So how do you look at this stuff? So the main thing is you have to realize that when you look at turbulence, you think your world is 3-dimensional. But actually, number of degrees of freedom that describe the fluid, there are infinitely many of them. So you have to go to what's called state space. We call it phase space so far. And you have to find some coordinates and how to look at it. And if you're smart and do it smartly, that's not important. But here is what happens. So this picture looks like dynamical system pictures from Strogat's book. You're willing to believe that it's a three-dimensional picture because it cannot be two-dimensional because lines cross each other, except in the central region that don't seem to, these pink guys don't seem to cross itself. But it's actually 64,000 dimensions, of which you have taken 3 cleverly chosen ones, which use intrinsic topology of solutions to look at it. And this is not one snapshot. This is 1,000 different videos because every one of them was a projection of one of these videos into 2 or 3 dimensions. You can look at it. You can look simultaneously into the fluid on the right, like a human plumber does, and look at its state space. And something is happening. So here is an example. Time is moving. Oops, you see something is happening. You have a dynamical system trajectory, which is one-dimensional line or curve in 64,000 dimensions. But, a curve is a curve. And it does weird stuff. It goes here and you realize, it gets really turbulent when it's close to this green stuff. And, I cut its tail so it doesn't fill up the whole thing. So this is a finite stretch of the trajectory. Then it jumps. When it's long, it's very fast. Done something wild here, does something wild here. And you start realizing that this wild thing can be given names because it's going close to the equilibria that you computed exactly this upper lower branch and nubis and God knows what. So that's what you learn by using dynamical systems vision, which people didn't do until 15, 20 years ago to understand fluids. Now we are fearless. We can live in 64,000 dimensions, and things you're learning in Strogat's are very useful. So then, story goes on, but basically the state space gets filled up with invariant things. So here is a periodic orbit, for example, that visits one region of state space and another region of state space, and it looks very turbulent, but by labeling the neighborhoods, you can actually give it a name. It's a thing that does a very special thing. And you can start out feeling the world of all possible kinds of weather, let's say, by a vocabulary of exact solutions. They're numerically exact. They can be computed to arbitrary accuracy, which describe turbulence. And then you can see that these solutions are explored by turbulence. So here's a turbulence solution, which came close to periodic solution, just accidentally. And it follows that you cannot distinguish 2 of them until it runs away, because this is an unstable periodic solution. So I told you that when we looked at subcritical Hopf bifurcation, there was this weird unstable periodic solution that you think you don't see, but that's not true. Turbulent systems explore neighborhoods of periodic solutions, and you can use them to describe this. And that's 10-minute summary. And now the important part of describing them is to look at the stability. and look at a variety of eigenvalues you can compute and describe your solutions by their stability that enables you to tell you which ones are important, and so on and so forth. And then you can get very nice portraits of turbulence. So here is something that you never see by looking at the clouds, but you do by looking at a state space that describes them. You get these beautiful behaviors in this turbulent, totally disorganized, crazy states by realizing that there are neighborhoods of unstable equilibria. So this is at the center of this region, which behave non-linearly. So very close neighborhood, we had linear approximation, but as we go further out, non-linearities come in and they curl the space. So you get this unstable manifolds traced out by spirals nicely, which for a while, and when you look at your state space for a very large while, distances comparable to largest distance in the space, organize all trajectories until they have a topological obstacle, some unstable orbit or something else that happens here. And then the hell turns loose and you start realizing you can patch up the behavior of these dynamical systems in arbitrary dimensions by using local patches like this one and gluing them together. So that's what's wonderful about this course, and that's why there is a Nobel Prize for it, because that's actually what people do today, when they're trying to understand climate or weather, in both cases, as extremely demanding applications. I will now stop this indoctrination session and go back to something I find very boring, which is chemistry.